I don't know if you've gotten billing and phone out of the way. So this is a specular lighting model, and it was first described in 1967, but it was its, I guess, final form came in 1982. So it's basically a well, this is sort of a little bit more complicated, but basically we're taking the sum of all the different n dot l's times a constant plus 1 minus a constant times r. I mean, that's what r stands for, and that's just one half of the equation. But basically, you don't really need to know this. The only form of the Cook-Torrance function that you need to pay attention to is this right here. Which is f times d times g divided by n dot l times n dot v for viewing direction. There's a pi sitting out front. So the funny thing about the Cook-Torrance function is that this pi really shouldn't be in this equation. So when we write it, you can put the pi in or you could take it out. It really depends on what you want to do. I will not be putting the pi in for this shader in this tutorial. So let's explain what F, D, and G are. So F is the big Fresnel effect, and it really was. I'm going to get into this a little bit later, but it is. You can think about it as a function or a output or a formula that basically tells you how much light is going to be refracted by an object or reflected by an object. So this would be important for surfaces or objects, or the surface of water, or an object like a glass, if you're modeling glass with water in it. The Fresnel formula is computationally heavy, so there is Slick's approximation of it. I will show you Slick's approximation when we get to the Fresnel. Well, I'll show it to you as we're adding in our Cook-Torrance function, but we're ultimately not going to be using the Slick's approximation in our shader, but I will have to use the Fresnel function when we first write the Cook-Torrance shader, so I will use six. So his formula is based on a reflectance value plus 1 minus reflectance value times 1 minus the halfway vector times the viewing direction to the power of 5. The reflectance value is going to be a property that you're going to set in your function up here, and the range of the property is going to be based on some real world examples, but we may end up having to tweak it later on. So the D in this equation is actually the roughness or microfacet distribution. So it's called, I guess it's called distribution, microfacet distribution, and that's why it's called D. But microfacet distribution is basically It's basically telling us how rough the surface is. So a surface is really smooth versus a surface is rough versus a surface that's quite rough, and a surface is really, really, really rough. This is Beckman's distribution function. That's just one of several distribution functions. There's a Newman distribution function, and there's an implicit distribution function, but the other popular distribution function is GGX. So the main two distribution functions that I look at a lot are Beckman's and GGX. GGX is a distribution function that's actually pretty popular with Disney. The Beckman distribution function actually looks pretty similar to Billin. So the reason why we have Fong, Billin, and GGX all up here is because there is a implicit distribution function built into Billin and Fong. So technically they are a microfacet distribution function, but they're also a lighting model at the same time. They're a full lighting model, but they don't use Fresnel, and they don't use this geometric attenuation that we'll talk about in a second. So the reason why we have the Fresnel and geometric attenuation is basically to create a lighting model that's actually physically accurate. If you don't have the Fresnel in there, Fresnel effect, you don't get one that conserves energy. So that's basically why we have to do that. But before we go to Cook-Torrance, I want to go back to the Billin and Fong model. So the what is actually working as a microfacet distribution function is the specular exponent. So it's actually this line down here. Because the specular exponent, or the shininess, can also be thought of as the roughness. So we increase the shininess, but in actuality you can think of it as decreasing the roughness. So if we look at our original shader, which is still currently using the Fong lighting model, when we look at the shininess, which I have it set to 0, shininess of 0 can be considered it could be considered roughness as being 100%. And so we don't get any shininess at all. So all we're looking at right now is the half Lambert, or not a half Lambert, but all we're looking at right now is the wrapped diffuse that we set up earlier. As I increase the shininess, we're decreasing the roughness. So in other words, we're going from a surface that was extremely rough to a surface that's less rough. And as we can keep increasing the power to, like, let's say 2, 4, 6, 8, 10, 12, 14, and so on, we're getting an extremely smooth surface, and we're also getting smaller highlights. Fong is a lighting model that creates extremely small highlights anyway. Oops, that was not 14. That's 14. So, as you can see, the roughness or smoothness can be thought of as the it can be thought of as representing the micro facets. So basically, it is built into those two functions, build and Phong, but we have a separate one. We have separate modular component distribution functions that we can add into the code, and this is how it was written in Beckman's paper in 1963. But this is not how it's actually going to look in our shader. There's no way we're going to have a tangent up here and another function to a power or anything like that. Or we're not going to be trying to type that out. The next thing is our geometric attenuation. So the geometric attenuation is more about, it's more about, let's see if I can, let's do a new one. So geometric attenuation is more about shadowing or internal shadowing. So you have a surface that's smooth, and then you have you have a surface that's, I just need to use a regular line here. We have a surface that's smooth, and this is perfectly smooth, like mirror smooth. And no surface is actually perfectly smooth, even mirrors, except for the ones probably in like the Hubble telescope, and then the ones that were used to catch gravity waves, I think, might be pretty much the smoothest mirrors in the world. But anyway, so for the roughness, the micro facets are modeled as these different size bumps, where some are larger, some are angular, some are kind of wiggly, and some may be square. That's not how these how the roughness is modeled. Remember, I had said in another video that in the models the roughness is assumed to be uniform, and we don't have any areas where we have a larger indentation or protrusion, or one that's pointy or something like that. They're all assumed to be uniform, and they're kind of modeled like this, being a sharp crypt and two sides. And so we have a normal direction for this side, a normal for that side, and a normal for up here, and for a light direction or our light cone flashlight. I don't want to get in the habit of using lasers for this explanation. Our flashlight, our reflected directions are going to consist of the same angle reflected off of this light, off of this surface. So you're going to have one reflecting off of this surface, and let's see, you can't reflect this way because that's just going to hit the geometry, so it's going to have to be reflected off of the normal. I'll have to be reflected this way so that the angle of light reflection from here to here is going to be equal to the same angle of light reflection from here to here, meaning that this angle, this is going to be the, actually, no, I did something wrong somewhere. Okay, so the light is hitting at this angle, and I think the reflection actually is going this way, but it's hitting another piece of geometry, so you don't get this reflection. So we have a reflection that actually doesn't appear. That would be going this way. So this one is a reflection that was canceled out. So we don't get any no, that's not right either. If I turn my head, this would probably make a little bit more sense. So the light direction actually is reflecting, but I think it's going to be reflecting this way, and it's not quite canceled out. It's kind of like this. And if you remove this arrow on this side, it would actually be directly in the middle, so that normal is still correct. Sorry about all that. And if I have my eye if my eye is over here, I'm only going to see light that hits this side, and since there's no light hitting this side, I don't see a specular reflection. But there is light bouncing this way, and so that'll in real life that light would kind of keep bouncing back and forth through this crypt and actually create sort of a global illumination, so I would still actually be able to kind of see this side, and so the diffuse lighting is kind of going to represent the global illumination over here, so you'll still be able to see it. It won't be pitch black because we have the diffuse lighting there, but I'm not going to be able to see a reflection. If my eye was over here, I will see some light because I'll have my eye is gonna hit right here, and I'm gonna be able to see the light. I'm going to be able to see all the light that's in this area bouncing off of this surface, and I won't see I don't think I'm going to see any of the specular component of the light off of that surface, because the reflection is all going this way from each of these individual photons of light. But I will see some light being reflected off of this surface, and so I'm going to see a bit of a highlight in this area, but I can't see anything down here. I can't see any specular down here, and I can't see any specular on that side. So the geometric attenuation is basically a function that's trying to decide how much light I'm not actually able to see from my particular viewing direction. So with my viewing direction being down here, I'm only able to see light coming from this area over here, but I can't see any of the light here and here. So it's basically trying to calculate how much light actually has actually made it, but I can't see it. There's another circumstance which could occur where I have a crypt here and my light is down here illuminating everything that is not being shadowed by this point here, and then my eye was up here. I'd be able to see all the light in this area, but then I would also see this unlit area. So now we're modeling how much light I can see and then how much shadow I can see, where in this situation all I can see is light, but I cannot actually see that shadow. So the the lighting model has to say, okay, well, I can see all this, and there was actually no light that shined down there because the lighting angle and the viewing angle is kind of similar. So I basically see 100% of the light that was reflected. In this case, I see 100% of the light that was reflected, but I also see areas that the light didn't get to. And then there's also another case where I'm looking at the light is going to be, well, my viewing angle is going to be my viewing angle is going to be a little bit more shallow, and I can see everything over here. But the light angle is coming down here, and it's a light cone, so this area is being lit up. But my viewing area is also a viewing cone, so I can see everything pretty much. I can see everything within. Why am I still yellow? I can see everything within this area, basically, until there's light shining down here, but I can't see it. So the model also has to take into account lights down here that I can't see. So the geometric attenuation, let's see, this is these are the different cases. So this, I think, is the one for the light is reflected without interference. The light is reaching the viewer, so that would be, so this 2 times n dot the half vector times n dot the viewing direction divided by the viewing direction times the half vector. That would be the case where I think this would be the case where I can see all of the light and none of the light is being occluded. In the second case, which is 2 times n dot half vector times n dot light direction divided by light direction times half vector would be the case where some of the light I can't see because the surface is blocking my vision. And so you take the minimum of these 2 functions, but you put a 1 out front. So it's a, I guess, it's a vector, so it needs three directions. And so this is how a Cook-Torrance shader looks. What's important is we start with the n.l, start defining n.l, and then we start calculating what n.b is, n.h is, the half vector, the half vector, we do a half vector dot product of normal vector, we do a normal vector dot product view direction, we do a view direction dot product the half vector, and then we want to square the roughness value, and the roughness value is going to be a property that we're going to have at the top of the shader, and we want to square it. It's going to be squared for use in the distribution function. I think most of the distribution functions use the squared roughness value, but I don't remember if GGX does. Well, we'll get to that when we start talking about GGX. So we first do our geometric continuation, and this looks like this might be this looks like maybe this is an implicit geometric continuation, because there's multiple geometric continuations. It's modular, just like the microfacet distribution function is modular. There's different versions of this as well. This looks like this is the implicit one. And then we go for the Beckman distribution function, and this is what the Beckman distribution function looks like inside of a gaming engine. We don't use it in this form. And then this is Slick's approximation for nil. And the FO is going to be the refract versus reflect, or angle or incidence value, something like that. I'll explain what that is when we come to that section. And then we just create the specular variable, which is equal to the Fresnel times the geometric continuation times the roughness, which is F times D times G. F times G times D. And we have divided by n dot B times n dot L. And in this one, they put in a pi. I'm not going to be putting in a pi. And then we do our final value, which is the light color, n dot L. And we're going to have specular, and then we're going to have these K values. The K value is down there to control the brightness of the Beckman. It's there to modify the microfacet distribution function. At least that's what it appears to be doing when I mess with it. It seems like it's there to, I think, keep the microfacet distribution functions values in correct range so that the shader behaves as expected. If you don't have it in there, it causes some problems. And in Unity, we're also going to be multiplying by the diffuse lighting. So this is a breakdown of what a Cook-Torrance shader looks like. So that's the end of this